So, like I said, this little Venn diagram looking thing is going to help us with always, sometimes, never. Let's fill it out, and then I'll tell you how this works. So all the figures we've been talking about fall under one major category. That category is polygons with four sides. What do we call polygons with four sides? Quadrilaterals. So these all fall under quadrilaterals. Hey, then we had a lot of these quadrilaterals that fell under one main subcategory. So a lot of the quadrilaterals, the one thing they had in common is that they were all what shape? Parallelograms. They were all parallelograms. So look at our overlapping circles to the right. That main circle is going to be parallelogram. And then within that parallelogram, we had subcategories of parallelograms. We had the rectangle, we also had the rhombus, and if you put all three of those together, what did we get? Square. The square, you got it. Okay, ignoring the kite right now, because remember I told you the kite was a little bit weird. Ignoring the kite. All right, we had another set of quadrilaterals that did not fall under parallelogram. Who remembers what those were? The trapezoid, excellent. So we had the trapezoid. And what was a subcategory of the trapezoid? An isosceles trapezoid. Okay, so I'll write out the rules for you and then I'll explain it. So if we are going small to big, it's going to be an always. If we're going small to big, it's going to be an always. If we're going big to small, it's a sometimes. And if the two circles have nothing to do with each other, what do you guess? It's a never. Good. So write that down and then I'll show you how this works. Okay, so I said small to big is an always. So see how the isosceles trapezoid is a small circle within the big trapezoid? So small to big. So an isosceles trapezoid is a trapezoid, always, sometimes, or never. You tell me. Small to big, always, sometimes, or never? Always. So an isosceles trapezoid is a trapezoid always, small to big. A trapezoid is an isosceles trapezoid, big to small, sometimes. And that makes sense, right? An isosceles trapezoid is a trapezoid, so it will always be a trapezoid. A trapezoid can be an isosceles trapezoid if it has some extra special feature to make it special, right? A trapezoid is a quadrilateral, small to big. Always. An isosceles trapezoid is a quadrilateral. Again, small to big, always. Do we get it? Okay, so I want you can just sort of write your answers on the side anywhere on your screen, maybe underneath, anywhere you want. I want you to zoom in and write it out for me, hold it up. So I'm going to ask you questions. You're going to tell me always, sometimes, or never. Okay. A parallelogram is a quadrilateral. A parallelogram is a quadrilateral. A, S, or N. Zoom in. Hold it up for me. A parallelogram is a quadrilateral. Perfect, 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 perfect. You got it. It isn't always small to big, right? A rectangle is a trapezoid. A rectangle is a trapezoid. Always, sometimes, or never. Good, 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 good. Good, good, good. You all got it. All right. A rectangle is a parallelogram. Always, sometimes, or never. A rectangle is a parallelogram. Good. Good, 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 good. All right, a parallelogram is a rectangle. A parallelogram is a rectangle. A parallelogram is a rectangle. Always, sometimes, or never. Excellent. Good, 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 good. It's a sometimes. A parallelogram is a rectangle sometimes. A parallelogram is a rhombus. Always, sometimes, or never. Always, sometimes, or never. Good, 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 good. All right. A rhombus is a trapezoid. A rhombus is a trapezoid. Always, sometimes, or never. Excellent, 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 excellent. All right. A rhombus is a quadrilateral. A rhombus is a quadrilateral. Good. 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 Rhombus is always a quadrilateral. Right. So small to big, always, but also a rhombus is always a four-sided figure, right? A four-sided polygon. All right. A rectangle is a rhombus. A rectangle is a rhombus. A rectangle is a rhombus. Actually, let me ask this first. A rectangle is a square. Let's do that. A rectangle is a square. Changed my question. A rectangle is a square. Good, good, good. Good. Good, good. Excellent. It says sometimes. A rectangle is sometimes a square. Why? Look at the Venn diagram, right? That square, isn't that within the rectangle circle? So a rectangle is a square, big to small. That's a sometimes. But also, just knowing your properties, right? A square, a rectangle, a square has all the properties of a rectangle. Since the square has all the properties of a rectangle can sometimes be a square if it has an extra special feature to make it better than just a plain old rectangle. Right, so rectangle is sometimes a square. A square is a rectangle. A square is a rectangle, always, sometimes, or never. A square is a rectangle, always, sometimes, or never. Your screen went black on me. Good, 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 good. No, I see some always and some nevers. I see some always, some nevers. A square is a rectangle. Look at the rectangle circle. Isn't that square within it? So it's small to big. What did we say about small to big? Always. A square is always a rectangle. And remember, what did we say? The square was the queen bee. She had every property of a parallelogram, every property of a rectangle, every property of a rhombus. So a square is always a rectangle, a rhombus, a parallelogram, because it has every property that they have. All right, let's do this. A square is a parallelogram. A square is a parallelogram. Good. Good. Good, 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 good. It's an always. A parallelogram is a square. A parallelogram is a square. Good. Sometimes. A parallelogram is a square sometimes, right? Big to small. Big to small within the same circles. Big to small sometimes. Okay, a rhombus is a square. A rhombus is a square. Good. Big to small within. Big to small sometimes. Good. A rhombus is a square sometimes. A rhombus is a square sometimes. A square is a rhombus. A square is a rhombus. Good. A square is a rhombus. Good. Always. A square is a rhombus always. Why? The square has every property of a rhombus. It will always be a rhombus, but also based on the Venn diagram, small to big. A small to big is an always. Right. So we did a rectangle is a rhombus. No, we didn't. We did a rectangle is a square sometimes. A square is a rectangle always. A rhombus is a square sometimes. A square is a rhombus always. A rectangle is a rhombus sometimes, always, or never. A rectangle is a rhombus sometimes, always, or never. I'm not telling you if you're right or wrong. I'm waiting to see everybody. I'm not going to tell if you're right or wrong. I'm waiting to see everybody's. So far, I don't see any always. I see some sometimes, and I see some never. So it looks like everyone has agreed that always is not an option. Do we agree? It's definitely not always. Okay, let's see. So a rectangle is a rhombus. I'm going to tell you it is sometimes. A rectangle is a rhombus if that rhombus is a square, because that's where they overlap. Okay, so a rectangle is a rhombus sometimes if that rhombus is a square. All right, what about a rhombus is a rectangle? A rhombus is a rectangle always, sometimes, or never. All right. It is a sometimes, same idea. A rhombus is a rectangle if that rectangle is a square. That's their joining thing. The square is linking the rectangle and rhombus together, because a square is always a rectangle and a square is always a rhombus. Right? So when can a rectangle ever be a rhombus? If that rhombus is special and it's a square. All right, are we ready to introduce the kite now? Where does the kite play into this? So what did I tell you last class? The kite and another quadrilateral had a relationship. Who remembers which quadrilateral the kite had a relationship with? Jeff? Trapezoid. Not the trapezoid, no, close. We did it. Demetri? The triangle? A triangle's not a quadrilateral, but that's okay. Nora? A rhombus. Do you guys remember I told you everything the kite can do, the rhombus can do better? Did we have this conversation? Yeah? Okay, good. So the kite and the rhombus have a relationship. What is the relationship? Well, remember, everything the kite can do, the rhombus can do better. Every single property the kite has, the rhombus has too, just better. So basically, the kite has properties individual, like one diagonal bisects the other. In a rhombus, both diagonals bisect each other. In a kite, the top two sides are congruent, the bottom two sides are congruent. In a rhombus, all the sides are congruent. Everything the kite can do, the rhombus says, hey, I can do that, but I can do it better. So what is the relationship here? There's a separate relationship. So generally speaking, a kite is not a parallelogram. So it does not have the properties of a parallelogram. So it does not fall under the parallelogram circle. But because everything the kite can do, the rhombus can do better, this creates a little bit of a gray area for us. It's a little bit shady. Why? Because now everything the kite can do, the rhombus can do better. A rhombus will always be a kite because it has all of its properties. Since a rhombus is always a kite, what does that mean? A kite can sometimes be a rhombus, right? But now that opens up a whole world of things. If a kite can sometimes be a rhombus, what does that mean? A kite can sometimes be a parallelogram if that parallelogram is a rhombus. Do you see how it now connects us to this whole circle? Right? So a kite is sometimes a rhombus. A rhombus is always a kite. What about a kite can be a square, always, sometimes, or never? Sometimes, right? Because a rhombus is sometimes a square. Do we see this now? Okay. So that will help you with all the always, sometimes, or never. So today's lesson, we are still working on all the quadrilaterals, but we're just going to do all algebra problems with these quadrilaterals. Next class, we'll do all proofs with these quadrilaterals. So let's see how this works. All right, in all honesty, how many people started memorizing the properties? Oh no. But I told you how important it was. This makes me so sad. It's horrible. I wish you would have lied to me. Okay, so we have a parallelogram. I tell you we have a parallelogram. What does that mean? We can use all the properties of a parallelogram. So what should we remember? Well, there's a ton of properties for a parallelogram, but now doesn't it seem like all we're really doing is finding angles, finding missing angles based on what they're asking us to do? So what do we know based on the angles? Well, we know the angles opposite each other are congruent. Do you agree with that? So the big angle S is congruent to the big angle L. The big angle C is congruent to the big angle A. But that's not going to help us find any of these individual angles. Like they're saying find angles 1, 2, 3, 4, 5, 6. Find the individual angles. Right, so I need to remember something else that will help me find the individual angles. Well, in a parallelogram, aren't the sides across from each other parallel? Opposite sides are parallel. That will absolutely help me find these individual angles because I'm just going to start looking for Z's. So look what I have here. Do you see that Z I just made? There we go. Nothing ever goes away, huh? Even though we're done with that chapter, it's not going away. All right, so what does that mean? What does that Z mean? If SA and CL are parallel, angle 5 has to be 60 degrees. If the arms of the Z are parallel, the armpits are congruent. So angle 5 is 60 degrees. All right, does anybody see anything else we can do to find these angles? It doesn't have to be in order. Anything you can do to find any of these angles.
Make another Z.
Good. Which way are you making a Z?
Standard Z way. Like not backwards,
like that?
Yeah.
Okay. So from S to A to C to L. Do we see that Z? All right, if the arms of the Z are parallel, the armpits are congruent. So what does that mean for us?
Angle 2 is equal to 40.
Angle 2 is 40. You got it. Okay, so let's erase this Z. All right, does anybody see anything else we can do? Angle 4 is 50 degrees. You got it. How'd you do that? You did another Z. Excellent. So we can do this Z from C to S. Oh, yep, from C to S to L to A. Do we all see that Z? So again, if the arms of the Z are parallel, the armpits are congruent. So that means angle 4 is 50 degrees. Let's erase that Z. Okay, does anybody see any other angle we can find? Good. Did you do a Z? Oh, I love that. Okay. So here, we know the opposite angles are congruent, right? Since all of angle A has to be how big? 40 plus 30, which is 70. So doesn't that mean all of angle C also has to be 70? So if the bottom part of angle C is 40, doesn't the top part have to be 30 in order to add to 70? Yeah, did anybody use a Z for this? You did? Yeah, you could have done a Z also. How could we have done the Z? So from S to C to A to L. Both ways you get the same answer. Okay, that's great. So now we got all those. Now let's go to angle 1. How are we going to find angle 1? Well, Do you all see this triangle that I just highlighted in yellow? What do all the angles in a triangle, the interior angles in a triangle, have to add to be? 180. Matt, could you take your AirPods out? Right, they have to add to 180. Well, I already have 30 plus 50, which is 80, which means angle 1 has to be 100 to add up to 180. So angle 1 is 100 degrees. And now for angle 6, you can do another triangle. Do you all see this green triangle I highlighted? You can do that and say, okay, well, a triangle has to add up to 180. Or, a little bit quicker, what's the relationship between angle 6 and angle 1? They're supplements, right? They make that straight angle. So either way, what do we get? That angle 6 has to be 80 degrees. You got it. Okay, let's do another one. All right, so number 2 is saying we have a rectangle. If they tell us we have a rectangle, that means we can use all the properties of a rectangle. So there's a lot going on here. If I'm looking at what I'm trying to find sides, I'm trying to find angles, I'm pretty much trying to find a lot of things. So I'm going to go through all the properties that I know of a rectangle, since they're basically asking me for a lot. So in a rectangle, I know opposite sides are congruent, so I'm marking that. What else do we know about a rectangle? Excellent. In a rectangle, all angles are right angles. There's also something else, and when we were marking up all the properties of a rectangle, I had marked something and I said, this is the telltale sign that this is a rectangle. Anytime you see this, it's going to be a rectangle. Well? So you're right, in a parallelogram, the opposite sides are parallel, but that's for all the parallelograms. So like a parallelogram, a rectangle, a rhombus, a square. So that's not our telltale sign that it's a rectangle, but it is true. The opposite sides are parallel, and that's important. All parts of the diagonals are congruent. Do you guys remember? In a rectangle, the diagonals are congruent, but because it's a parallelogram, they bisect each other. So this is such a huge part. You really, really need to know this. In a rectangle, all 4 parts of the diagonals are congruent. That's a huge thing in a rectangle. Okay, so let's see what they're asking us. The first thing they're asking us to find is PN. Isn't that a part of the diagonal? But isn't EP 8 inches? So if EP is 8 inches, what do we know about all 4 parts of the diagonal? They're all 8 inches. So PN is 8 inches. Okay, then it's asking us for UP. Well, isn't UP also a part of the diagonal, which means it is also 8 inches. Okay, then we want to find JN. Well, JN is the full diagonal. Well, what's the full diagonal? If JP is 8 and PN is 8, the full diagonal has to be 16. All right, now they want us to find X. Let me show you how we're going to do this, because this type of question will come up a lot in rectangles. So in order to find X, do you all see this triangle I'm highlighting in green? Triangle PNU. Okay, in triangle PNU, angle P is 50 degrees. And this is also really important because we really couldn't do this without it. In triangle PNU, aren't the legs congruent? Because all 4 parts of the diagonals are congruent. If the legs are congruent in this triangle, what do we know about the base angles? They're also congruent. So this angle X and this angle y have to be congruent. Well, how am I going to find x and y if they have to be congruent and angle P is 50?
The parts of the angles are bisectors, so they're bisecting the right angle.
Oh, I think you're confusing a rectangle and a rhombus. You're right, in a rhombus. In the rhombus, they bisect the angles, and in a square, they bisect the angles, but not in a rectangle. So like this 90 can be split into like 40, 50, 60, 30. It doesn't have to be split in half. Laura? You got it. So remember, doesn't a whole triangle have to add up to 180? Since the legs are congruent, the base angles are congruent. So we know these bottom two angles, x and y, have to be congruent. We know this top angle is 50. So we're going to do 180 minus 50. That's 130. And then since x and y have to be congruent, we're going to do 130 divided by 2, and we will end up with 65. So angle x is 65. That means angle y is also 65. I'm going to jump to W. I'm going to jump to W over here. Well, isn't the big angle U 90 degrees? So if y is 65, what does that mean for W? How are we going to find W? 90 minus 65, you got it, which is going to be 25. Excellent. All right, now we want to find angle Z. The quickest way to find angle Z right now is to use this triangle. Uh-oh. My husband's calling me. 1 second. He butt dialed me. Okay. He made me nervous. Okay, so we're looking at this triangle. Once again, look at this yellow triangle. Aren't the legs congruent? If the legs are congruent, what else are congruent? Base angles. So if one base angle is 25, the other base angle has to be 25. Do you think it's important to know the properties? Yes. All right, let's keep going. Let's talk about rhombus. Okay. I'm going to go through, it looks like we're asked to find sides, we're asked to find angles, so I'm going to go through all the properties of a rhombus, and I'm going to mark them up. So in a rhombus, what do we know about all the sides in a rhombus? They're congruent. In a rhombus, all sides are congruent. Do we agree just because it is a parallelogram, in a rhombus, opposite sides are parallel? So we'll mark that. All right, somebody tell me something else about a rhombus. Anything you remember about a rhombus? Nobody remembers anything about a rhombus. Somebody remembers something. Awkward silences don't bother me till somebody remembers.
The diagonals bisect.
Yeah, excellent. The diagonals bisect the angles. But let's take it even a step before that. Because a rhombus is a parallelogram, aren't the opposite angles congruent? So the big angle N is congruent to the big angle U, and the big angle B is congruent to the big angle R. And Kaylee told us the diagonals bisect the angles. So the diagonals by N are congruent to each other, and I'm sorry, the angles by N are congruent and the angles by U are congruent, but because N and U are congruent, all four angles are congruent. Also, the angles by B are congruent to each other and also congruent to the angles by R. Tell me something about the diagonals of a rhombus. Tell me something about the diagonals of the rhombus. Are all four parts of the diagonals congruent? In a rhombus, are all four parts congruent? No, that's only what? A rectangle, and by default then a square, right? So that's not in a rhombus. So what about a rhombus? What about the diagonals of a rhombus? Because it is a parallelogram. The diagonals do what to each other? They bisect each other. So that means these two are congruent and these two are congruent, not all four. Oh. I need to know one more thing about the diagonals. There's one more thing that's important about the diagonals. It's about how they intersect. Yeah, the diagonals are perpendicular, which means we have four right angles right in the middle. All right, so now we can start finding some things. First thing we want to do is find angle 1. Well, because the diagonals are perpendicular, angle 1 has to be how many degrees? 90. Write it in. All right, now we want to go ahead and find angle 2. You know what? Before I find angle 2, I actually want to find x. Before I find angle 2, I'm going to jump down here. I want to find x. Oops. Any ideas on how I can find x? Well, where do you see an x? Not Kaylee, not Nora. They're holding up the class today. Their backs must be hurting. Somebody else. This is not a difficult question. I'm asking you, where do you see x? Well, good. Angle n. Our eyes are open. Yay. All right. So angle n. We see an 2x expressions right here by n. Well, didn't we say that the two angles by n are congruent? Because in the rhombus, the diagonals bisect the angles. So how am I going to solve for x? We set these two equal to each other. So in order to find x, I'm going to say 7x minus 6 is equal to 5x plus 10. I'm going to subtract that 5x. And we're going to have 2x minus 6 is equal to 10. Add that 6 over. 2x is equal to 16, so x will equal 8. Now that I know that x is equal to 8, now I can go ahead and find the measurements for these two angles by n. So if x is 8, 5 times 8 is 40 plus 10 is 50. That means these two angles by n are 50 degrees. All right, let's go ahead and now find angle 3. How am I going to find angle 3? Do you all see this triangle? In this triangle, oh, I deleted one of my markings, sorry. There we go. All right, in this triangle, are the legs congruent in this triangle? No. If the legs are not congruent, are the base angles congruent? No. So how am I going to find angle 3 if it's not like legs to base angles? How am I going to find angle 3 if it's not legs to base angles? Jeff, how am I going to find angle 3?
You're going to add 90 plus 50.
You got it. 90 plus 50 is 140. Then what do we have to do? Subtract that from 180. So angle 3 has to be 40 degrees. Okay, let's keep going. Well, if angle 3 is 40 degrees, which other angle has to be 40 degrees? Omar, if angle 3 is 40 degrees, which other angle is 40? 2, because they're marked congruent. All right, couple of different ways we could find angle 4. First way you can find angle 4, do you all see this blue triangle? Yes, do you guys see that? In that blue triangle, you have a 90 and a 40, which tells us that last angle has to be 50. What's another way we could have found angle 4? A Z, excellent. You could have found angle 4 by this Z. Do you see that yellow Z? If the arms are parallel, the angles in the armpits are congruent, so that angle 4 and 50 have to be congruent. So angle 4 is 50 degrees. What about angle 5? What's the measure of angle 5 and Y? Good. Why is angle 5 50? Because they're congruent to angle 4. Exactly. All right. The last thing we need to do is find the perimeter. When we find the perimeter, don't we have to add all the sides? Well, I have one side is 14. In a rhombus, aren't all sides congruent? So that means every side is 14. So what are we going to do? We're going to do 14 times 4, which is 56 units long. Y'all need to memorize the properties. It is going to be very tragic, your grades on this quiz and test, if you do not memorize the properties. All right, let's keep going. Let's go to a trapezoid. All right, trapezoid is nice. Why is a trapezoid nice? Because a trapezoid only has one property. The one property is that the bases are parallel. I've already marked the parallel bases. So how are we going to do this? I'm going to start off by finding angle 1, just because it says it first. So you could start off anywhere you want. How am I going to find angle 1? Do we all see this triangle? A triangle has to add up to 180. So what am I going to do? I'm going to do 70 plus 25, which is 95, and then 180 minus 95, which gives us 85. All right, now we want to find angle 2. Well, I can use the parallel lines to find angle 2. Do we see that Z? So that means angle 2 is 25 degrees. Right? So now that I know angle 2 is 25 degrees, tell me, can I use this Z to find angle 3? Why or why not? Can I use this Z to find angle 3? Kaylee?
The sides are parallel.
Excellent. Remember, the Z only works if the arms are parallel. Are the arms parallel here? No, so this Z doesn't work. If I can't do a Z, how else would I find angle 3? Jeff?
100 plus 25.
You got it. Do we see this triangle? Triangle adds up to 180. So to find angle 3, we're going to do 180 minus 125, and we are going to get 55. All right, let's go on to number 5. It's a kite. I'm going to go up, mark all the properties of a kite. Remember, the kite's the worst one. All right, so in a kite, the top 2 sides are congruent and the bottom 2 sides are congruent. Somebody tell me anything else they remember about a kite. Anything at all. Well, good, excellent. The big angle I is congruent to the big angle E. What else? You got it. The diagonals are perpendicular, so we have 4 right angles in the middle. What about the long diagonal and the short diagonal? What happens there?
Short ones are congruent.
Yes, so the long diagonal, so the parts aren't diagonal. So a diagonal has to go from like one vertex to another. So we can't call like angle I to like this dotted diagonal, but I know what you mean. The long diagonal bisects the short diagonal. In a kite, the long diagonal bisects the short diagonal, so these parts are congruent. Hey, tell me something else. Jeff?
4 and 6 are congruent.
You got it. 4 and 6 are congruent, and the 2 angles on the other end are also congruent, but not all congruent to each other. All right, let's do this. So, first thing we want to do is find angle 1. We found angle 1. How many degrees is it? 90. Right, now we want to find angle 2. Well, in order to find angle 2, it's a little bit sneaky here. Do you all see that big triangle IKE? Do we see it? IKE? In IKE, what kind of triangle is this? Isosceles. The legs are congruent. If the legs are congruent, what else are congruent? The base angle. So what does that mean for angle 2? 35 degrees. It's like everything we have ever learned is coming back. All right, so now I want to jump to angle 4. And in order to find angle 4, I'm going to use this triangle that I'm highlighting in green. So I have a 90 and a 35 in a triangle. So if I have 2 out of the 3 angles, can I find the last angle? Absolutely, because we're adding up to 180. So we're going to do 90 plus 35 is 125, and then you do 180 minus 125, and we get 55 for angle 4. Well, if angle 4 is 55, which other angle has to be 55? Angle 6, you got it. Now I'm going to jump to angle 5. I'm going to jump to angle 5. For angle 5, I'm using the big triangle ITE. Once again, in that big triangle, aren't the legs congruent? If the legs are congruent, what else are congruent? Legs are congruent, then? Good. Base angles are congruent. So that means angle 5 has to be how many degrees? 50 degrees. All right, now let's go to angle 3. How am I going to find angle 3? You got it. We're going to add 50 and 90 and subtract that from 180. We're using this blue triangle to find angle 3. So that means angle 3 is 40 degrees. All right, I want to now find IE. Well, do we agree that I to this middle point that I didn't name is 4 units long, 4 inches long? So that means the dot to E is also another 4 inches long. So that means all of IE has to be 8. All right, IT. Well, IT is congruent to ET. So IT has to be 10. And then IK is congruent to KE. So IK has to be 7. All right, this will be the last one we do for today. Your homework starts at number 10. Your homework starts at number 10 and you finish it through. You don't have to do any textbook pages. You don't have to do any textbook pages. You're just starting at number 10 and going straight through. All right. The last problem we're doing is, where is it? The isosceles trapezoid. Okay, the isosceles trapezoid. So they're telling us that HE and GF are legs. So that means HG and EF are the parallel bases. There is something you need to know about an isosceles trapezoid. You cannot use this in proofs, but you can use it in algebra problems. In an isosceles trapezoid, do you guys remember the diagonals are equal to each other? The full diagonals. So like EG is congruent to HF. Well, always what ends up happening in an isosceles trapezoid, the top two parts of the diagonals are congruent and the bottom two parts of the diagonals are congruent. You can use that only in algebra problems, not in proofs, because it's not really a property. It just always works out that way. All right, so here we have that EJ is x plus 5 and JG is 2x minus 1. All of HF is 13. All of HF is 13. So we want to find, which one? E to J. Well, if I want to find E to J, we have to solve for x. Well, isn't all of EG equal to all of HF since the diagonals are congruent? So that's where we're going to start. So we're going to say EG is congruent to HF. So what does that mean? That means x plus 5 plus 2x minus 1 has to equal 13. So we're going to have 3x plus 4 equals 13. 3x is equal to 9, so x will equal 3. Now that I know that x is equal to 3, we know EJ is x plus 3, 3 plus 5, which is 8. What about JG? How long is that going to be? 5. And the last thing we want to do is we want to find HJ. Well, which segment is HJ congruent based on that little loophole I told you about the diagonals? Good. HJ has to be congruent to GJ. So if GJ is 5, HJ is also 5. I don't think I have time to do a square, but let's just get there. Everyone go to number 9. The square is the easiest one. The square is the easiest one because in a square, it has all the properties. So not only are all sides congruent, all angles are right angles, all parts of the diagonals are equal, and the diagonals are perpendicular. And also, because it is a rhombus, what do the diagonals do to the angles? Because it's a rhombus, don't the diagonals bisect the angles? Since the diagonals bisect the angles, each part is how many degrees? 45, I heard it. All right, let's just go through this real quick then. All right, so angle 1 is 90 degrees. Angle 2 is how many degrees? Angle 2? 45. Angle 3 is how many degrees? 45. You get the gist, right? Angle 4 is 90 degrees. Squares are the easiest ones. Okay, so remember, your homework are numbers 10 and then starting at 10 and then finishing up that packet.